Hi, and welcome to our lesson 4.7. Today we're going to be talking about the inverse trigonometric functions. And folks, the inverse functions are the ones that you use to find an angle if you know the value of sine, cosine, or tangent. So they are the invert functions, not the reciprocal, right? The invert functions. I have some information that I've just written on about the three curves. This is a sine wave. And we know that this thing has a domain from negative to positive infinity. But we also know that if we're going to talk about the inverse function, see how a horizontal line would hit that in more than one place? That won't be a function. In order to make the inverse trig relations to be functions, folks, what we have to do is limit the domain of sine. We want to get one full from up to down, and so the principal values that they use for the sine are, so we're going to limit the domain of sine to, limit the domain of the sine to -1, actually it's negative pi halves to pi halves, and that will get us one full cycle of up to down, right? All the values are covered there. For cosine, to get that same total from all the positive values, all the negative values, the domain is limited to 0 and pi halves. That gets us all positive and all negative, so we're from here to here. And then for the tangent, we limit the domain to negative pi halves and pi halves. Again, that gets us one full, all positives, all negatives. So now we can talk about the invert of these functions and what their graphs might look like. And I'm going to do sine inverse here. Really what I'm going to do is the trick that we've used before. I'm going to invert that table. So the sine wave, its inverse function has these values. At -1, it's negative pi halves. At 0, it's 0. And we're just switching x and y here. At 1, it's pi halves. So pi halves, you guys, that's 3.14 divided by 2. It's about 1.57. So when x is -1, y is about -1.5 here. When x is 0, y is 0. When x is 1, y is about 1.5 again. So right in there. And the way that the curve works on this one, it's up and then down. So it kind of looks like a little tiny squiggle, and that's the sine invert function. The cosine invert, the table that we're going to use is the backwards of what we had written up there. So 1, 0, and -1. That was weird. -1, 0, and 1. At -1, we have pi, so about 3.14. At 0, we have pi halves, about 1.57. And at 1, we'll have 0. So -1, we're up about 3 right in there. At 0, we're at about 1.5, so right in there. And at 1, we hit at 0. And the curvature for this one is down, up. Okay? Here's our tangent inverse. This one is going to be a little bit weird because those asymptotes, so if I were to write the table, I would have asymptote at pi halves, right? So I'm going to do that. Asymptote at negative pi halves. 0 and 0, and then asymptote and positive pi halves. Well, yeah, what is all that asymptote stuff? Well, I know that this curve is going to go through here, and I also know that the domain on the inverse function is the same as the range on the input, right? inverse's domain is the same as this. So it goes from negative to positive infinity. And folks, we've limited this curve, right? We've limited its domain. So the range on our invert is limited from negative pi halves to pi halves, or at 1.5 about, and negative 1.5, we have asymptotes, right? Horizontal asymptotes this way, or this time. And that curve slides along here, comes up through here, slides along there. And there are the graphs of the inverse functions. I will tell you, I'm not a big fan of graphing these. You probably won't see them again, okay? However, I do want us to be familiar with how the inverse functions work. So we can find exact values for inverse functions using our trig reference tables. I hope that you will. If we want to find the sine inverse of 1, then we either are going to look at our table or we're going to think sine has to do with y's, and where y is 1 is straight up there. Since we have on the invert functions limited our domains, the theta, the angle that we name, has to be between, for sine it's negative pi halves and pi halves. And it so happens, folks, that we are looking at pi halves right here. So the sine inverse of negative 1 is pi halves. Okay? The cosine inverse of root 2 over 2. Theta is the angle whose cosine is root 2 over 2. And I know those are the 45-degree marks. Our theta has to be, for cosine, has to be between 0 and pi. And for us, in between there, the 45-degree mark or the pi-fourths mark is where cosine is root 2 over 2. Our last one says find the tangent inverse of negative root 3. We got to think theta is the angle whose tangent is equal to negative square root of 3. And we want to remember for tangent, theta must be between, it's negative pi halves and pi halves. Good. So now we look at our reference sheet, or we think, from looking at my reference sheet, I can tell you that my theta is, the place where this happens between those two is at negative pi thirds. That would be negative 60 degrees. Okay? You can also use your calculator's inverse functions to get approximations as opposed to exact values like we have. I'm going to call that calculator up, and we can use our calculator's inverse functions to get approximations. These are exact, right? Approximations happen when you start using decimal points and estimating. The cosine inverse of negative 0.8, so we'd second and cosine negative 0.8. And ladies and gentlemen, it's going to make a difference to us whether our calculator is in degree or radian mode. I'm going to check mine right now. Mine is in radian mode, so my answers will be in radians. Okay? The cosine, or the angle whose cosine is negative 0.8 in radians, is approximately 2.50 radians. Many of us would rather know in degrees, so that's easy to find. Same keystrokes, second and entry will get you that. And go ahead and hit enter, and here's the degree measure of that angle. So that's approximately 143.1 degrees. You can do the same thing for tangent, obviously, and I'm still in degrees. So second tan 3.2 is around 72.6 degrees. Very good. And we've got some rules. This is a snapshot of something that was in your textbook, so you'll be able to see this in your textbook probably better than it's showing here. but there are rules for composing functions, and they're pretty straightforward, you guys. This equation right there says, give me the sine of the angle whose sine is x. Well, the angle whose sine is x answers that question. The sine of the angle whose sine is x. It's x. The sine inverse. So this says the opposite way. It says, give me the angle whose sine is the sine of x. That also is x. So we're composing here, kind of playing little games here. And what we have to be careful about is that our answers are within the domains for the inverse functions. So this first one says, find me the angle whose sine is the sine of negative pi thirds. As long as negative pi thirds is between negative pi halves and pi halves, then we're okay, and it is, folks. So this would equal negative pi thirds. Pi thirds are smaller than pi halves. Our next example asks us to find the cosine of the angle whose cosine is 1.6. And folks, I'm afraid there's a problem with that, because if you think about the cosine function, see, we're looking at this pattern, cosine of cosine inverse, x has to be within the range -1 to 1, and 1.6 is not in that range. Or, if you think about it, there is no angle that has a cosine that is 1.6. So this one is not possible. This one says, find me the angle whose sine is the same as the sine of pi, except we have to be inside this range, and pi isn't inside that range. So we got to do some thinking on this one. The sine at pi, so I got to draw the curve just so I can remember. The sine at pi, so here's pi, here's 2 pi. Sine starts here, goes up. Okay, so the sine at pi is 0, and the place where we find a sine of 0 in this range is when theta is 0. I know that seems kind of odd, folks. The question said, find me the angle within this range whose sine is the same as the sine of pi. The sine of pi is 0, and the place in this range where the sine function is equal to 0 is when the angle is also 0. I know that's a little bit weird. Alright, we're going to be evaluating some composite trig expressions here using a right triangle, which to me this makes more sense than what you just looked at. We want to find the exact value of the sine of the angle whose tangent is 3/4. And tangent inverse, folks, is defined over the range negative pi halves to pi halves. So we're in these two quadrants. If the tangent is positive, we have to be in Q1. And you'll remember that tangent is y over x. So we have some angle out here whose tangent is 3/4. That is, its x is 4, its y is 3. Pythagorean theorem will tell us that its radius is 5. And what we are supposed to do is find the exact value of sine for that angle. So the sine of theta will be opposite over hypotenuse 3/5. Very good. Do that here. We want the exact value of the cosine of the angle whose sine is 1/2. Sine is also defined in Q4 and 1 from negative pi halves to pi halves. And we have the sine this time is 1/2. So the y, sine is y over r. The y value is 1. R is 2, and we need to find the cosine, so we need the x here. Pythagorean theorem says 2 squared minus 1 squared, I'll write it out. 2 squared is equal to 1 squared plus x squared. That's 4, that's 1, so we're 3 equals x squared, and x equals the square root of 3. Now we can say that the cosine and cosine of theta, the cosine of our angle is √3 over 2. And we use those invert functions to do that. Good, I hope that you'll get out there and try the U-try at your earliest convenience.